So let's go ahead and combine all of those properties that we've talked through with simplifying roots, extracting roots, rationalizing denominators, and simplify all these expressions here. And let's see how we kind of go through that process. So this first example, I'm seeing a root 15b times root 15b. If we're working with square roots and we're multiplying the same exact thing, what we can do is just simplify that to the value that's underneath. Because what we would end up having, just to show some process here, is our square root 15b times 15b. So we'd have this 15b squared. And what we would have is this cancellation between the root and the exponent of 2, and we would just be left with what's underneath. What was the base of the exponent of 2? In this case, 15b. Okay, with this one, where I'm going to go ahead and get started is multiplying the values outside the radicals. So we'll have a negative 20. And I'm going to go ahead and combine the values that are underneath the radicals. So we'll have 6 times 2, which is 12. B squared times b cubed, which with the exponent properties, we add the 2 and 3, so that's b to the 5th power. Now I'm going to think about re-expressing what's underneath the radical to see if I can grab anything out of there. So we're taking a square root. So 12 could be expressed as a 4 times 3, because I like taking that square root of 4. And then b to the 5th, could think of that as b to the 4th times b. So with that, I have this negative 20 outside, and then we're going to multiply with square root of 4 is 2, times, I'll go ahead and write this as a rational exponent, so b to the 4th, but taking the square root would divide that by 2. And you can see we're going to get a nice whole number there. So we took care of the 4 and the b to the 4th underneath the radical, but I still have a 3 left over, and I still have 1b left over. So underneath the square root, we're still going to have a 3 and a b. So this will be negative 40b squared root 3b. And that'll be all simplified. And I know it's simplified because the values outside of the radical are multiplied, the values inside the radical are multiplied, and also if I look underneath that radical, the radicand is completely simplified. There aren't any roots that I can extract because square root of 3 doesn't do anything, square root of b doesn't do anything. Okay, let's look at this root 10 times 4 plus root 2. So we're going to distribute just like we usually would. So this is going to be 4 times root 10 plus root 10 times root 2, which would be root 20. Now root 10, and what you could do is a quick prime factorization. That's coming from a 2 times 5, so there's not going to be anything we can extract from that. So 4 root 10 is stuck. But 20 I could re-express as a 4 times 5. So that would be a 4 root 10 plus square root of 4 is 2, but then we still have a 5 trapped underneath. And then that would be it. As a reminder, with adding or subtracting radicals, you have to have the same radicand. So if this was 4 root 5 plus 2 root 5, then we could combine those to a 6 root 5. It's just like having 4x plus 2x being 6x. It's very similar to that process. But if they're different, this would be a scenario that would be like having 4y plus 2x. We can't add them together because they're fundamentally different. Same thing with the root 10 and root 5. So we would just leave them separated just like that. Okay, with our next one, we're going to distribute a root 15. So let's see, root 15 times 5. So 15 times 5 is 75. And then we have a multiplying underneath, plus root 15 times 2 is 30, and then an a. So 75, it's good with the 25 times 3, and then we still have an a there, plus 30, 5 times 6. I'm not seeing much in the prime factorization, so 5 times 6, which is a 2 times 3. I'm not seeing any pairings coming through, so that's going to be stuck as a root 30a. So with the first one, root 25 will bring a 5 out front, and then we have a 3a stuck underneath, plus root 30a. And I'll just stay like that. Okay, root 2 over root 10. Few ways to go about this, but let's just go with rationalizing the denominator. I don't want to have a radical in the denominator, so I'm going to multiply the numerator and denominator by a root 10. So that's going to make a root 20 over root 10 times root 10 is a 10. 20 I could express as a 4 times 5. And with that, square root of 4 will bring a 2 out front. 5 will still be trapped underneath the radical, and then dividing by 10, which 2 divided by 10 will leave us with a 1/5. So we have a square root of 5 over a positive 5. And we leave it just like that since we rationalize the denominator. And we could do the same thing with this next one. Let's go ahead with that. Oh, I'm going to simplify it first. Why not do it a little differently? Okay, up in the numerator, I have the square root of 3 times n squared. 3 is going to stay trapped underneath, but that n squared would be like having n to the 2 divided by 2. So I can extract an n, but I still have 3 trapped underneath the square root. And then divided by 3, and then square root of 2n to the 4th. Well, I could think of that as n to the 4 divided by 2. So that's going to extract an n squared, but we still have a root 2 stuck underneath. So that's simplified to n root 3 over 3n squared root 2. And then if I go with rationalizing the denominator, I need to multiply by a root 2. So up in the numerator, we'll have n times root 6 over 3 times 2, so 6n squared. And we'll have an n cancel across the numerator and denominator because they're both outside the radical. So we'll just have a root 6 in the numerator over 6n in the denominator. So with that, we just canceled out an n like that. All right, a few more examples here, more with addition, subtraction. So just like looking for like terms and what I was saying up above, like you could think of this as x plus y plus x, because that root 2 and root 2 are fundamentally the same because they have the same radicand. Same index, same radicand, so we can combine them together. So just like how we would call that 2x plus y, we do the same thing here, where it's I have 2 of those root 2's. So I would have 2 root 2 plus root 5, and they would stay separated because I cannot add those together because they're not like terms. So it's just like adding like terms, but we're looking for same index and same radicand in order to combine them. This one, these are all like terms because they all have root 3, so same index, same radicand. So what I'm really thinking of is I have -3 of them, and I'm taking one away, so that's -4, but then adding 3. So this is a -1 root 3, combining those together. So just thinking of the numerical coefficient as a -3 minus one of them plus 3, just looking at those values out front, and that led to a -1. Okay, with this next one, can't combine them, but we have some simplifying we can do with that 54. So let's see, a -√6 minus 3 and 54 could be separated to a 9 times 6. I like that because I know the square root of 9. So -√6 minus 3 times square root of 9, which is 3, and then we have a 6 trapped underneath. So this is a -√6 minus 9√6, and now we can combine them to a -10√6. So again, just thinking of it as like -x minus 9x would give us -10x, same idea. All right, one more example here. So that root 54 I'm going to simplify with that 9 times 6 again. with 45, that'll come from a 9 times 5. That sounds good to me. And then minus 3 root 5. Nothing to do with that 5 there. Okay, 3 times root 9. So 3 times 3 is 9. And then we have a root 6. Minus 3 root 5. Minus 3 root 5. We can combine those 3 root 5s. So we still have a 9 root 6 on its own because it can't combine anything. And then a minus 6 root 5. And then we leave it just like that. And that's how you could simplify some radical expressions.